if it is
Okay.
so likewise, so means the unit vector of one coordinate system in terms of unit vector of other coordinate systems. So,
Mm.
so that is by taken by the projection. So that's very important. Then moving next, we have gone through the space derivative of the vectors. So what were the three vectors and scalars? So what were the space derivatives we have covered?
Gradient, divergence, curl.
Well, and there is one more Laplacian, which is
Like,
applicable on both scalar as well as vector. Okay, there is one more Laplacian operator, del square. Do you remember?
yes, sir.
Yes. So that also we have covered. Then two very important theorems we have covered. And what were those two important theorems?
Go slow. Sorry, theorem. Divergence theorem and Stokes theorem.
Gauss divergence theorem and Stokes theorem or the Stokes law.
Stokes theorem.
Okay. So these two were the very important theorem uh, uh, by which we can convert the line integral to surface integral and the surface integral to the volume integral. Right?
Yes, sir.
Yes. So up till here we have seen. Then moving to the next, we studied the electrostats. We studied the Coulomb's law of electricity. We studied the Gauss law, the concept of electric field. Then what was the statement of Gauss law?
Gauss law means the electric flux
Mhm.
equal to charge enclosed by a closed
Yeah,
surface.
so net outward flux is equal to the total charge enclosed by the surface. And and what is its differential form?
Means del dot D equal to rho V.
Yes, so that is the differential form of the Gauss law in electrostats. Okay,
Okay.
and that is also known as the first Maxwell's equation, right?
Okay. Yes, sir.
Yes. Then we have seen the that electrostatic field is conservative in nature, which simply means its
Hmm.
curl is, if it is conservative in nature, then its curl is
Zero.
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 That we have seen. So then proceeding next, we also have seen the Poisson's and Laplace equation. Yes.
Hmm. Yes, sir.
What was the Poisson's equation?
Um, del square V is equal to minus rho V by epsilon.
Very good. And what was the Laplace equation?
Del square V equal to zero.
Very good. So this we have seen. Then we have seen some little bit about the current density. There we have seen the point form of Ohm's law. What is the point form of Ohm's law?
Um,
What is the point form of Ohm's law?
I forgot. Sir.
Del dot J. Okay, remember the point form of Ohm's law. Here once. Del dot J is equal to sigma E.
Okay.
Oh, sorry, not del dot. Sorry. J is equal to sigma times E. Just let me write it here. J is equal to sigma times E. Can you see on the board?
Yes, sir.
Yes. This is the point form of Ohm's law.
Okay.
Okay.
Okay. Okay.
Where sigma is the conductivity and E is the electric field, J is the current density. Clear?
Yes, sir.
Yes. Then what was the equation of continuity? In that same chapter, we have studied the equation of continuity.
Yes.
Tell me.
That J plus J D1.
Sorry? Yeah, once again, please.
No, sir, I forgot. J plus JD.
No. You totally forgotten. Go through the revision of that. That's also very important. Equation of,
Okay.
and this we have studied. You can't say we have not studied. We have studied. See,
Mm.
del dot J is equal to minus of del rho v.
Yes, draw V by.
We have studied or not?
Yes, sir. Yes, sir. Yes, sir.
Yes, we have studied. So remember, this is equation of continuity. Equation of continuity. Okay?
Yes, sir. Yes.
So this we have said. So remember, del dot J is minus of del rho v upon del T. Okay? Then we have seen the magnetic field. In magnetic field, that is magnetostatics, that is the magnetic field due to a steady current. So that was given by Biot-Savart's law. I hope you remember what is Biot-Savart's law.
Yes, sir.
Okay. Then we have seen the Ampere circuitous law. That was the another Maxwell equation. What was its integral form of the Ampere circuitous law?
Um, closed integral H dot
Which
ds
integral?
closed line integral
Very good. Closed line integral.
H dot dl
Mhm.
equals to
Mhm.
uh, J dot surface integral J dot ds.
Very good. Open surface integral.
Uh,
And what is its point form?
del cross H equal to J.
Very good. So that is Ampere circuitous law. Del cross H is J. Very nice. Then moving next, we have seen the Faraday's law of EMI. So very quickly, just
Yes.
I want to come to the main topic because all these are required there. That's why also I am
Hello.
using it. It is helpful always to revise the things in short. Okay. So
Okay, sir.
Faraday's law of EMI. So what does it say? The Faraday's law of EMI.
Means the EMF induced will be
Mhm.
proportional to rate of change in
Rate of change in rate of change in hello.
magnetic flux.
Yes, whenever it's simply
Hello.
a simple statement. Whenever there is a change in flux, the EMF is induced in the loop. Yes?
Hello.
Yeah, whenever there it simply says,
Hello.
hello, can you hear
Hmm.
me?
Yes, sir.
It simply says, whenever there is a change in magnetic flux, there is an EMF induced.
Hmm.
So, what was its differential form?
That is del cross E
Mhm.
equal to minus del
Del cross.
cross E
Mhm. Del cross.
equal to
Mhm.
yeah,
Del cross is
minus dou B by dou. Uh,
yeah minus of del V upon del T.
uh,
So fine. So this we have studied, and last we have studied was the modified Ampere circuitous law. That is the concept of displacement current, and that says del cross H is J plus del D upon del T.
uh,
Yes or no?
yes, sir.
So, okay, it was good to revise, and most of the things you remember, and two things which you have forgotten that also has been revised. One was the equation of continuity, this you had forgotten, and another was the point form of Ohm's law. Okay,
Okay.
so remember, the next time if I ask you, means you should be knowing this. Okay,
Okay, sir. Okay.
that would be better for you. Fine. So now we will start, means we will see actually why we studied all this. Because the entire subject name is electromagnetics. Yes or no?
Yes, sir.
So this is actually the now this EM, the electric field and magnetic field, they are, see, go to the just very previous concept, just very means previous, just in the previous class concept. We discussed that time varying magnetic field is producing a time varying current. Yes or no?
Yes, yes, sir.
And then, but of course, that if current is time varying, then by the Biot-Savart's law, it will produce a time varying magnetic field. Yes or no?
Yes, sir.
So see, try to imagine and analyze the field, the time varying field is producing a current, and that current is again producing a field. Yes or no?
Okay. Yes, sir.
Yes. So these two are now interrelated. These two are now oscillating in nature, because first the time varying field that gives a current. That current is time varying. Again this time varying current giving again a time varying field. Again a time varying field. Current field. Are you getting my point?
Yes, sir.
So what is actually happening? Actually happening is that electric field and magnetic field are now propagating in space in the form of wave, very popularly known as electromagnetic wave. Is it clear till now?
Hello?
Yeah, is it clear till now?
I didn't heard, sir.
Didn't heard. Why? There was network problem.
Uh, yes, sir.
Okay, okay. What I said in the last
Hmm.
slide, that this time varying field is producing a current. Time varying
Hmm.
current is again producing the time varying field. So this
Ah,
magnetic field and electric field are now propagating. They are oscillating in space and propagating through the space in the form of popularly known as electromagnetic wave. Is it clear?
yes, sir.
So this is what you see, the field at the large distance from the charges and current sources. So see the first very known equation, del cross H. That's why I went for the revision of all this, because we will be requiring all this. The Maxwell
Okay.
del cross H is J plus epsilon times del E upon del T. You see. So see, in the
Okay.
you see this equation very carefully, the left hand side, it is the space derivative of h. Yes or no?
Hmm. Yes, sir.
And the right hand side, it is the time derivative of e.
Hmm.
So a space derivative of h is giving, or in other words, we can say the time derivative of e is giving the h in the form of its space derivative. Yes or no?
Okay.
So see, this is what I am saying. That
Hmm.
on another equation you will see. See, this one, del cross E is, and this is nothing but that Faraday's law minus del B upon del T. Yes or no?
Yes.
Yes. So if you see the same phenomena but contrast, here time derivative of H is giving the space derivative of E.
Okay.
Variation of E with respect to time is generating the H, and variation of H with respect to time is generating the E.
Okay. Yes.
So means these two are now generating each other. If H is varying with
Okay.
time, E is generated. If E is varying with time, H is generated. So these two are now not these separate individual quantity, rather they are all together. They are together, they are simultaneously being generating each other. So they are now
Hmm.
propagating and simultaneously existing there in the space in the form of
Okay.
electromagnetic wave.
Hmm.
So this is what, see the statements also. For a straight conductor, the magnetic field is given by Ampere's law. That is, we know. At
Hmm.
large distance or very high frequency, see the magnetic fields are a function of time comma distance. See here. This lags I. due to the propagation time. This is very, very important. So at the high frequencies, this magnetic field, it is lagging the current. And see, why it is lagging the current? Because if you see, they actually, when H is being produced at T comma D, at that time, the current is lagging by a factor of distance by speed.
Okay.
Okay.
Huh.
So, so, so this is what the very, very important point is here. The modulation of current is producing the rate of change of this magnetic field.
Okay.
Okay.
Okay, sir.
And similarly, the variation of the electric field with time is producing the H. So this is what this two statement means. Last few minutes I have been repeating this by different means, that these two statements are very, very important. This is why
Okay.
or how this EM wave, this is from where the concept of EM waves comes into the picture.
Okay.
EM means electromagnetic wave. This electromagnetic wave is carrying the power, energy, it is having the properties, and due to this EM wave, we are able to talk on the mobile, we are able to even attend the class right now. This all is happening due to this EM wave, electromagnetic wave. Am I clear?
Yes, sir.
So see, let us see the just some basic working phenomena. A static charge produces the radial field lines. This already we know. Okay. Then you see constant velocity, acceleration, and finite propagation speed distorts the field line. Again, this is here. And I will show you this why we are writing del square E upon del T square, or how or we are writing. Uh, better to see, better to see the next slide. That will give you the better idea. Yeah, here for the time being, just you see how the means it is being propagated. You see, electric field in plane of the page, and magnetic field is out of the page. So see how this structure is being drawn for the magnetic field. I think this little bit we have covered while we were talking about the field of the solenoid. So this field lines are looking like this. If you see around the
Okay.
center, how it is around the center, how is the shape, and as you go away from the center, see how it gets changing.
Okay.
So, and one very important point is here, that this field propagates at a velocity of light in free space. And what is the velocity of light?
3 into 10 raised to 8.
How it has been derived? It was experimentally seen that C is 1 upon under root mu naught epsilon naught. What is the value of mu naught?
4 pi into 10 raised to minus 7.
What is the value of epsilon naught?
10 raised to minus 9 by 36 pi.
Yes, exactly. So if you put these two values here, multiply them, take their square root, take the inverse of that, you would be getting approximately 3 into 10 to the power 8 meter per second.
Okay.
Now, I'm having a question here from you. Suppose the wave is not propagating in free space, rather it is propagating in some medium whose permeability is mu, and the it is permittivity is epsilon, then whether the speed of the EM wave will be less or more.
Mm, less.
Can you justify it? Why or how?
Uh, uh, means mu 0 and means it will become mu 0 mu r
Mhm.
into epsilon 0 epsilon r.
Very good. Very good. Proceed. Very good. Proceed.
Then
You are going in the very right direction. That's very good.
then it will be a high value, na?
No.
Uh,
See,
0.
you are going right, but I don't know why you got confused. Perhaps you are not doing the paperwork. That's why maybe you got confused. You are doing right. That is not the high value. It is, you said, sorry, you said very rightly that it is 1 upon mu naught mu r times epsilon naught epsilon r. Agree?
Yes, sir.
Yeah. Then I can, this is the velocity, then I can rewrite this equation as 1 upon mu naught epsilon naught times 1 upon mu r epsilon r.
Yes.
So this value I know, 3 into 10 to the power 8.
Yes.
Yes?
Yes, sir.
So this is being divided by some constant. Yes or no?
Yes, sir.
This will be always less. Yes or no?
Yes.
Agree?
Yes, sir.
Yes, because this is now constant and I'm dividing it by something. So of course this will be less. Even if I am dividing by the 1.5, this will become less. Yes or no?
Yes.
So, so mu r epsilon r. So this will decrease by a value of 1 upon root times mu r epsilon r.
Okay.
But the point, in any other medium apart from vacuum or the free space, so the velocity of EM wave is maximum in the free space and which is equal to the velocity of light.
Okay.
If the medium is anything other than any general medium other than the free space whose uh, field intensity whose permeability and permittivity are mu and epsilon, then it will reduce by, but here be careful, it will not reduce by mu r epsilon r, rather it will reduce by under root mu r epsilon r. Be very careful. Okay,
Okay, sir.
as I have shown you in the derivation also, that under root mu r epsilon r. Yes,
Yes, sir.
any doubt?
No, sir.
So now we will go through the equation of the EM wave. So see the some small derivation here and see what I went for revision was this purpose. You see each and every equation is being used here. First equation, del cross H is J plus del D by del T. Which equation?
Uh, J plus
Yes.
dou d by J plus d modified Ampere's law.
Newton law. Okay. So see that's why I went
Uh,
revision. From here we will
JC plus JD.
yeah. Then this one. Which equation?
Del cross equal to minus dou d by
This one.
dou t. Faraday's law. Second one, Faraday's law.
Very good. That is the law of EMI.
Okay. This one is Gauss law,
Gauss law in electrostats. And
electrostats. This one is delta to 0 is
this one is
it's, uh,
Marketer.
Gauss law in magnetic stat.
And see, this one I asked, but that time
Equation.
you have missed it. But see, that's why I was going through the revision because all this will come into picture here. So this one is already we have seen,
Equation of continuity.
and these two relations we know they are not known by the law, but they are the constraint. B is equal to epsilon times E and B is equal to mu times H,
H.
and this one is also known as
Ohm's law, point form of Ohm's law.
So can you see all those equations which I asked you for the first 10-15 minutes has to be used?
Yes, sir.
Yes. So, okay. So we have collected all this and then we will proceed. We will see the stepwise how to we are proceeding. So first see in free space, see from here, in free space, sigma is 0, J is 0. See, in free space, the current density is 0 and conductivity is 0. Okay.
Mm, mm.
So see, so what will be the changes? J is 0 means this equation, the equation number, the first which was written, the first equation actually, this will become del D upon del T. Yes or no?
Yes, sir.
Yes, because J goes to 0. And of course, del cross E will remain same as minus of del B by del T. Any doubt?
No, sir.
Then see the next step. Here, taking the curl on both sides of this equation, equation 2, taking the curl on both sides of this equation. So, once again, do you remember there was an identity curl of vector?
Del cross E is equal to del dot del E minus del square E.
Very good. Gradient of divergence minus z. Very right. So, but thing is only one thing I think, yeah, yes, grad of divergence minus curl of vector. Yes, you have spoken right. So that is what it has been used here. Del cross E is equal to C minus of, first we have taken the curl on both sides. So we will write the minus is there, del cross del B by del T. Till here it is clear. See the derivation, this is very important. That's why I am discussing this derivation. It takes the time, but it is
Okay.
important. We will reach to some very nice result. Means very meaning, meaning carrying result. So up till here it is clear?
Yes, sir.
Yeah. No doubt?
No doubt.
No doubt. Very simple. B can be written as mu naught times H. Yes or no?
Yes.
Then mu naught times H. So now it becomes the del by del T of del cross B. We can write this as here. These two are interchangeable by the rule of mathematics. This del by del T and this del are interchangeable. Means this you can take here and this del you can take inside. Are you getting my point?
Yes, sir.
So interchangeable, I am writing del upon del T times del cross B. See here, right?
Yes, sir.
So now B can be replaced by mu naught times H,
Yes.
minus of mu naught del by del T del cross H, right?
Okay.
And we know that del cross H is equal to del D upon del T. Yes or no?
Yes. Yes.
Because J is 0, right?
Hmm. Yes.
So we have substituted here del D upon del T. So del by del T,
Okay.
it will become del square,
Yes.
and D is nothing but epsilon times E.
Yes.
Minus mu naught epsilon del square E upon del T square, right?
Okay. Yes, sir.
On this side still we have not replaced, just in the next step. This side it is still del cross E, curl of vector, right?
Okay.
So see, just so curl of vector can be written like this. The uh,
Yes.
gradient of divergence minus like this, as you have already.
Yes, sir.
So here it has been written grad of del dot E minus del square E. Now you see here del dot E. What is the value of del dot E?
Uh,
Del dot E is equal to rho.
Row.
Yes or no? Because
Yes, sir.
del dot E is better to say rho upon epsilon. Not rho upon epsilon.
Okay.
Yes,
Uh,
but rho is 0 because free space.
mm,
Yes or no?
yes.
So this term will go to 0. Try to understand please. If any doubt you may ask, I will repeat. 0. So now minus minus gets cancelled out because this goes to 0. So minus minus will get cancelled out. Yes or no?
Yes, sir.
Now see the very, very important equation, and this is the three-dimensional wave equation. And see why what we have done. Try to understand. This is now see this equation. Both sides it is containing only E term. Both sides it's
Okay.
containing only E term. But previously, what was
Hmm.
the problem in the previous equations? That one side, if it was something like this in the previous slide, if it was del cross E is equal to minus of mu naught times del H upon del T, and other equation was del cross H was J plus epsilon times del E plus del T. Yes, it was there.
Yes, sir.
So here
Yes.
you see, they were the not means decoupled, means one was carrying the E and H, another was also carrying the H and E or E and H. So, so,
Hmm.
so such equations are called as coupled equation. Here we have decoupled the equation, and now we are getting the equation only either in terms of E or in terms of H. If you
Okay.
we started from here, just I am going back to the slide. Sorry. We started from here taking the curl of this equation. If you take the curl of this equation and you go on substitution, then you will reach to the del square h is equal to just like here, del square h is equal to mu naught epsilon naught del square h upon del t square.
Hmm.
So you can
Okay.
decouple, and this two equations. Are you getting my point? What I'm trying to say? I'm trying to say that if you decouple the equation by taking the curl of the another equation, you will get del square h is equal to mu naught epsilon naught del square h upon del t square. See, both side it is h now, and both side it is e now. Are you getting my point?
Okay.
And these two
Yes,
are
sir.
representing the wave. This is representing the propagation of wave in terms of electric field, and this is representing the propagation of same wave in terms of magnetic field.
Okay.
And they are called as the Gibbs-Helmholtz wave equation. Gibbs-Helmholtz, they are called as Gibbs-Helmholtz wave equation.
Okay.
Or many books are writing only Helmholtz wave equation. Getting the point?
Yes, sir.
Yeah. So this is the second order del operator, and here it is
Hmm.
one constant, that is mu naught times epsilon naught, times second order partial derivative of same electric field with respect to time. So this is showing the propagation of the wave with respect to time in the three-dimensional in the form of electric field, and similarly if it is h here and h here, then it is the propagation of the wave in the form of electric field in the three-dimensional, and these two are known as the Gibbs-Helmholtz wave equation. Am I clear up till here?
Yes, sir. Yes, sir.
Any doubt?
No, no.
Very good. So see, so from here you can see del square A is same, this del square A upon del T square. So finally, so see, from here, now this is a traveling wave. This is an equation of the traveling wave. What do you mean by the traveling wave? Traveling wave means its variation with respect to time. And see, it is not at a constant position. If you see its nature, it is propagating, means its displacement is changing in space with respect to time. That is the meaning of this traveling wave. Are you getting my point?
Okay. Yes, sir.
So see, the general solution in the mathematics, the general solution of this such equation is shown like A is equal to, if the equation is of this format in terms of A, then it is A is equal to A naught times as a function of Z minus Vt. Now from here you should be very careful. Z minus Vt. So see, what which this is representing wave propagating in positive z direction. See very carefully. Here it is z. So it is and here it is negative. So this is representing
Okay.
a wave traveling in positive z direction. Very, very important. If it becomes plus here, then this represents a wave traveling in negative z direction. Are you getting the point? Hello?
Yes, sir.
Are you getting the point? Hello?
Yes, sir.
Am I audible now?
Yes, sir.
So did you get the point?
Yes, sir. Means this negative means in positive direction.
Hmm.
Positive, then it's negative direction.
So see, this was the one dimensional wave equation. For the two dimensional,
Hmm.
it becomes only the double derivative of this function. So and so likewise, we can have the a naught v square f double dash z minus vt. So this is a traveling wave where v is given by, see here, 1 by mu naught epsilon naught. Here actually epsilon naught is missing, it is 1, and that is what I said. If you put the values of mu naught and epsilon naught, you will get approximately, you may check it using your calculator. You will get
Okay.
approximately 2.997, exactly 2.9979, which can be approximated as 3 into 10 to the power 8. And this is nothing but a speed of light, also called as c.
Hmm.
Am I clear?
Yes, sir.
So the important aspect we are discussing right now. So
Hmm.
see, now the wave equation. Let us suppose that it is of the sinusoidal nature. Ex, now very, very important. So I am stressing the things means they are having the importance. If somebody is
Okay.
writing Ex, you see Ex means only X component and it is traveling in which direction?
Positive Z direction.
Negative z direction. Here one thing should be known. See, while only X component is there, you see Y and Z component is 0, such wave are known as uniform plane wave.
Okay.
That's why if I go back to the very, very previous slide, means for the today, then the heading was there, uniform plane wave propagation. Did you notice?
Yes, sir.
Yeah. So what is the meaning of a uniform wave? Uniform wave means, let me explain a little bit more. Actually, there can be many more derivations, but I'm not going into everything detail. That is not also required. See, but still I will explain the maximum, which would be helpful for you. This electric field can be actually function of three coordinates, any three, it may be rho phi z, x, y, z, and third is the time. Because we saw that
Okay.
requiring the time, then it is producing EM wave. Yes or no?
Yes, sir.
It can be a variation of x, y, z and time. But for the
Hmm.
sake of simplicity, we are confining ourselves to the uniform plane wave. So uniform plane wave either ex or ey or ez will exist and it may propagate in means we will see and I will let you know actually what is happening. E and H, I will let you know in the upcoming slide also. E and H are perpendicular to each other and
Hmm.
the direction of propagation is perpendicular to the plane containing E and H. Are you getting my point?
Okay.
So here, if here
Yes, sir.
Ex is there and it is propagating in Z, so it is but of course that Hy is there.
Okay.
Because Ax cross Ay will give you Az. Yes or no?
Yes, sir.
Yes. So if Ex is there, it simply means Ey and Ez are 0. Hy is there, it simply means Hx and Hz is 0. Here a little bit it is conceptual. Please try to understand. If you doubt, be frank to ask. Don't hesitate. Because if you don't understand this thing, the
Okay.
entire is waste.
Yes.
Everything we have studied to understand this thing only. Those were just the means what casting type of the movie.
Okay.
Actual movie is this one. The UFT.
Okay.
Or you may say the climax of the movie is here only. All those were just like this to be okay. There is a hero, there is a heroine, they met and okay. But here is the climax of the story. So once again I'm repeating. E can be or H can be function. Hello? Hello? Hello?
Hello.
Yeah. Once again I'm repeating that E can be sorry. Hello?
Hello.
Yes. Yes?
Hello.
Yes. Anything you
Uh,
want to share?
no, sir.
So I think there was some network issue once again, right? Hello?
Hello.
Am I audible?
Yes, sir.
I think for the few seconds there was some network issue.
Okay.
So once again I'm repeating the electric field can be function of x, y, z, comma t.
Mm.
But for the uniform plane wave, only one component is supposed to exist and vary with respect to time. And perpendicular to that will be the magnetic field component. Are you getting my point?
Yes, sir.
So very important. You may see here this thing. Then it has been derived. Finally, see what type of equation you are getting. You are getting C cos of beta times z minus bt del by del z square. It has been differentiated. So you are getting the minus beta square sine of z minus bt. If you consider this equation, if you will differentiate it two times. So of course, so it is the beta square z minus bt. So this is representing a wave propagating in positive z direction. Yes or no?
Yes, sir.
You see, sinusoidal variation in E or H is solution to the wave equation, that Helmholtz wave equation. Okay. So the
Okay.
basic summary of the entire wave equation is that only one component of E and H will exist. They are always perpendicular to each other and direction of propagation is perpendicular to what? Tell me.
Perpendicular to both of this.
Yes, the wave will always propagate in a plane perpendicular to E and H.
H.
Yes or no?
Yes, sir.
Yeah, very important. Very important. So this was all about the basics we have discussed. See, the same thing has been written in a different way. Consider a uniform plane wave propagating in z direction. See, what is the direction of propagation?
Z.
Yeah. So, and it is saying that E is independent of X and Y. Means which component of E is existing?
Z.
Z. But here, that is what it has tried to show. Let's see. Only Z is existing. But if you see the equation, that is what they have proved, that Ez is 0. Ultimately, Ez will also come to
Okay.
0. Ez is constant, is not a wave. Means this is what this idea is trying to convey, that it can never be possible that E or H component can have, E or H field can have a component in the direction of propagation of wave.
Okay.
Are you trying to get my point? Are you trying to catch the?
Yes, sir.
Yes. It is never possible for the electric field and magnetic fields to have a component, listen very carefully, to have a component in the direction of propagation of wave. It can never be possible. Yeah,
Okay.
it will always be perpendicular to that. So if Ex is existing, Hy will exist and they will propagate in Z.
Okay.
If Ey is existing, then Hx may exist or Hz is existing and they will propagate in direction of X. Ay cross Az will give you Ax, yes or no?
Yes, sir.
Yes. So if Ey is existing, Hz will exist and they may propagate in X or they may propagate in negative X also. Then in that case, Ey and this Hz, H minus Z will exist. Likewise, it is there. Okay.
Okay.
Very, very important. The questions are being asked. So be careful. If you doubt, you ask me. So that's what the conclusion has been given. That's what I also said. The same thing. He has no component in the direction of propagation. See very carefully. Third time I'm repeating this statement. That it can never be possible for the E or H to have a component in the direction of propagation. Keep this in mind. Never ever it can be possible. Am I clear? Say loudly.
Yes, sir.
Yes. So
Yes, sir.
such waves are called as uniform plane waves. Right?
Yes, sir.
Yes. So orthogonal, that is already I have told you, they are perpendicular to each other. So nothing to do here. Now see the hello.
Yes, sir.
Now see the important relation. What is the relation between amplitude of electric field and magnetic field? Here you see a relation. Hy is equal to under root epsilon upon mu naught. So if I ask you what is Ex upon Hy? Ex upon,
Root of mu naught by epsilon.
sorry?
Root of mu naught by epsilon.
Yes, always remember the mu naught upon epsilon naught. See Ex upon Hy. Many time I am saying that it is, if it is X, this will be Y, and they may propagate in
Z direction.
this ratio under root of mu naught upon epsilon naught. If you put here the value 4 pi into 10 to the power minus 7, what is the value of epsilon naught?
10 raised to minus 9 by 36 pi.
Yeah, or in other words, 8.857 into 10 to the power
854
minus
into
12.
10 raised to minus 19.
No, minus 12.
Minus 12. Okay. Minus 12.
If you put this value, this will come approximately 120 pi. And very, very important. Or in other words, this is approximately 377 ohm. This unit is ohm. Means this is a resistance, and this resistance is known as intrinsic impedance. Very, very important term. So the ratio of Ex upon Hy in a free space is always a constant of approximately 120 pi, known as intrinsic impedance, denoted by eta.
Okay.
Intrinsic impedance. So if you know the Ex or Hy, you can find the other one. If you know the Ex, it is 377 times eta for free space. Once again, for
Okay.
free space.
Okay.
In any other
Ah.
medium, this will go to mu naught mu r, and this will go to epsilon naught epsilon r. Yes or no?
Okay, sir.
In
Okay, sir.
that case, impedance will increase.
Okay.
If impedance will increase, then velocity will decrease. Impedance means this is the resistance. This is the resistance offered to the speed of wave.
Okay.
So, and that from here also the same theory is verified that for any other medium, the velocity of wave will decrease.
Decrease.
Why decrease? Because its intrinsic impedance of the medium will increase.
Increase.
This,
Okay, sir.
this impedance is the resistance offered by the medium to the velocity of wave.
Wait.
And what is its value for the free space?
377 ohm.
Yeah, or 120 pi. Same. Pi is 3.14. So if you multiply the 120 by 3.14, that is approximately 376.8 or 9, something like that. That is approximately 377. So Ex, so E by H is always a constant. And what is that constant known as?
Intrinsic impedance.
Intrinsic impedance. Remember this. These are all very, very important concepts I am telling you. Here it, all I have mentioned here, but already I have told you. See I told you this symbol, yes or no?
Yes, sir.
Yes, eta, mu naught upon epsilon naught. So see, it has been proved why it is ohm. Volt per meter, ampere per meter. Meter gets cancelled, volt per ampere. This is nothing but ohm. Yes or no?
Yes.
Yes. How much is the value?
377 ohm.
377. E by H is 377 and E by B, another very important relation, E by B. So see, B is mu naught times H, yes or no? Yes or no?
Yes, sir.
Yes. So E by H is under root mu, mu naught epsilon, mu naught by epsilon, and mu naught is divided. So it becomes, you see, and mu naught is outside. You take inside, this becomes mu naught square. So it becomes 1 by under root mu naught epsilon naught. Yes or no?
Yes, sir.
So E by B is always C. E by B, but
Okay.
it's very, very slight difference. E by H is 377, but E by B is 3 into 10 to the power 8. See the huge difference.
Okay.
Can you observe the huge difference? Are you able to?
Yes, sir.
Yes, very. If you do a slight mistake, everything will go wrong. Yes or no?
Yes, sir.
Okay, so let me see today where we can stop. Oh yes, this I will cover in the next class.
Okay.
So you had your dinner?
No, sir.
No. Why? So late.
Uh-huh.
Okay, so tomorrow also you are having the class, right? So fine. Sorry, so tomorrow you are having your office, right?
Yes, sir. Yes.
Okay. So tomorrow means would you be able to attend the class at the same time, 9 to 10,
Yes, sir.
or that 6:30, something like that?
9 to 10.
9 to 10 would be better. Okay, okay. No issue.
What, sir?
No, means 9 to 10 would be better, or that 6:30 would be better.
9 to 10 will be better, sir.
Okay, fine. Then it's better for me also, because sometimes, as I told you today, as I was on the way, the all of a sudden the means tire got punctured. Then there it took me
Okay.
45 minutes, 1 hour to get it repaired and all that. So
Okay, then the last day of this year was hectic for you.
Activities have become all of a sudden, so it's a little bit. So no issues. It is a part and parcel of the life. It happens. Okay. So wish you a very happy new year. May God
Same to you, sir.
thank you. So may God fulfill all your wishes and hope you always come with the flying colors in the upcoming time. All your hard work comes with some good result in your life. So
Thank
all
you
the
so
best.
much, sir.
Okay. I wish you all the best. Okay. Have a good time. Enjoy. Uh,
Yes,
tomorrow,
sir.
we, tomorrow again we will meet. Okay.
Okay, sir.
Okay. Thank you. Have a good time.